All right. Good morning, everyone, and welcome to the July edition of AFMS seminar. And apologies for the technical issues that caused some delay to the start of the seminar. Anyway, so today in this session, we are lucky to have Professor Chris Keylock from Loughborough University. And Chris will be talking about enhancing understanding of turbulent flows using the Schur decomposition of the velocity gradient. Chris, the floor is yours.
Great, thanks very much, Morgan. Thanks very much for the invitation. And on this cover slide, I've just made a reference to a couple of people who funded this work, Loughborough and JSPS, and a number of collaborators and also people who've very kindly hosted me while I've been undertaking this work. And today, what I'd like to primarily focus on, when I can get my screen to change. Oh, there we go. It's just been a bit slow. First of all, I'd just like to go through a little bit of background on the velocity gradient tensor. Consider the Schur transform approach. Look at how it can be very helpful for actually understanding for some key results in turbulence. And I'll do one particular case, which is an alignment issue with vorticity and strain rate. And then look at results for various flows and finally conclude with some sort of thoughts about how turbulence modelling can potentially be improved using this framework. Okay, so just a little bit about me very quickly. Loughborough is here, right in the centre of England. I don't actually live in Loughborough itself. I live a little bit towards London. I'm actually from the best county in England, which is Devon, which is the one in pink on the map. It's actually one of the few areas with World Surfing Reserve standard surfing. So not big waves like often you guys have, but fairly good technical ones at least. And lots of Paleolithic remains and lots of scone and jam. And this is the difference between us and Cornwall, the other county in the southwest. Which way round you put the jam and the cream is the crucial difference between those two counties in my home area. Okay, and Loughborough itself is perhaps best known for sport. Here's the world rankings for sports subjects. You'll see the university I did my master's in fourth, two of your universities in third and second, and Loughborough currently top on these sorts of things. Okay, so moving into the substance of the talk then. So the VGT, the velocity gradient tensor, is found by starting off with the Navier-Stokes momentum equation and taking the spatial derivative. You end up therefore with, if you're assuming incompressibility, as I will be throughout today's talk, apart from a slight movement away from it at one point, if you assume that, you end up with this following equation for the velocity gradient tensor A, where what we've done in this formulation is split out the isotropic part of the pressure Hessian, which is this trace A squared over 3 times identity matrix term, and the deviatric part of the pressure Hessian. So that those are separated out is quite conventional in this approach, as we'll come on to in a little moment. And yeah, that's therefore the definition of H, where you can see that part subtracted. So there's a number of key papers in this field from authors from Australasia, particularly work done by Andrew Uy with some colleagues, and also the very famous paper by Perry and Chong from 1987. So those papers are well worth reading if you're interested in this topic. So given that one has a tensor by taking these gradients, then logically the first thing perhaps to look at is its characteristic equation, given here where the eigenvalues are written as lambda. And the first thing to note is that P will be the trace of the velocity gradient tensor, which is 0 for incompressibility. So people don't really talk about P too much unless they're doing compressible fluid mechanics. The focus is on the second invariant variant Q and the third invariant R. And if you look on the right-hand side, we've got the kind of famous QR diagram with different regions delimited there. And it's worth noting that if you can define the strain rate in terms of the velocity gradient tensor and also the rotation rate, And if you then translate those definitions into the eigenvalues, you find that Q is the difference between the entropy and the total strain rate. And you find that R is the difference between the strain production and the entropy production. There's another relevant quantity, which is the discriminant function, which I'm using here as a capital delta, QQ plus 27R squared over 4, which delimits this boundary in the QR diagram. Essentially, why is this important? It delimits regions of the diagram with real eigenvalues, which lie below this line, and regions with complex eigenvalues that lie above it. As a consequence, and there's another figure which I can't see because I'm seeing all of you guys underneath this part, but I think it should be saying over there that this is the Vier-Foss tail, the right-hand side of this, because the QR diagram preferentially concentrates down that right-hand side. And so there's typically two ways of thinking about this diagram that depend on your perhaps disciplinary background. If you're a mathematician, you'll say that there are 4 regions on this diagram, essentially dictated by the sign of R and whether or not you're above delta or below delta. So regions 2 and 3 get merged together, regions 1 and 5 get merged together. If you're an engineer, you typically say the 4 regions are dictated by the sign of R and the sign of Q. So you merge the regions 3 and 4 together and regions 5 and 6 together. I'm quite a fan of actually doing neither and actually keeping 6 discrete regions, as I think they will have actually different characteristics. And perhaps that will come across a little bit later on. Okay, so a key motivation of this work and why we separated out the pressure Hessian the way we did earlier comes back to this difficulty in Navier-Stokes, the local versus non-local problem. A problem that particularly reared its head perhaps in the 1920s, 1930s, when Albert Einstein was looking for a postdoc to work on his equations, and that person was Bob Creighton. And he turned around to Bob Creighton and said, well, look, my equations are 4th order nonlinear, so let's start off with Navier-Stokes. They're only 2nd order nonlinear. Let's solve them and then crack on with my equations. And of course, Bob Creighton spent his whole career trying to do what he'd been briefed to do as a quick aside problem by virtue of the fact that the non-locality is the key technical difficulty often with Navier-Stokes. And Koji Okitani wrote a classic paper with Kashiba in 1995 on this, which is essentially saying that when we look at the pressure field, we can separate it into this isotropic part that we've already defined and this non-local part. And this non-local part requires us to essentially take this integral over all space. And thus, that's really where the difficulty in Navier-Stokes comes from, because it's really an integral differential equation, not just a set of partial differential equations. From our work, this has issues because you could see earlier that we could express the local part in terms of the trace, of a squared, therefore related to q. That's not true for the non-local part. We need to model that in a more sophisticated way. And that was really shown in a classic paper by Brian Cantwell in the early 1990s. He wrote down the evolution equations for the 2nd invariant Q and the 3rd invariant R. And then he said, well, okay, let's work with this as an Euler problem. So we'll kill off the viscosity term. And let's get rid of the non-local effects that are coming into this problem from the pressure Hessian. So we'll blank off the viscous terms. We'll blank out the non-local terms, and we got this really nice model of 2 coupled ODEs that give us some characteristics for turbulence. So how successful is that model? Well, here's a diagram from Charles Menevaux's annual reviews on this topic from 2010, and you can hopefully see that wherever you start on this diagram, apart from the origin, you're going to end up in this bottom right-hand corner. So this gives us an explanation for why this Vier-Foss tail is so predominant as part of the distribution function for turbulence, because this simple model will end up in that bottom corner. And essentially all of the work in this area since has been trying to improve this model, and thus that ultimately comes down to a high Reynolds number, trying to deal with the deviatric part of the pressure Hessian in an appropriate way. And just to illustrate those 6 regions from one of our papers, some work done by Paul Beaumard, here's the PDF, and you can see it's matching this general pattern of a peak at 0 where things don't shift from those equations, or an extension down the bottom right on the Vieux-Fosse tail. And we've also just on the diagram just shown topologically what these different regions look like a bit, so you get a sense of the sort of strong entropy regions 1 and 2, and the sort of strong straining regions down at the bottom in 4 and 6. So we can then actually try to plot the 3 groups of terms. So you've got the QR diagram repeated on the left-hand side, but this is from some actual data rather than the idealization that you saw from Charles's work earlier. Then you've got the viscous term in the middle diagram, which is trying to essentially collapse everything back onto the origin. The right-hand term, the deviatric pressure term, is much more complex. You can see that, for example, some of the fluxes are counter to the directionality of the QR solution, particularly in that top right corner, what I was calling region 1. You'll see that the probability flux is going counter to the left-hand side diagram, where it's going essentially always clockwise around to that bottom right corner. So this shows why it's so difficult perhaps to capture some of this complex nature of the deviatric part of the pressure Hessian and its influence on Q and R. So I guess one way people have then tried to do this is they've done their dynamic analysis, as we've just been looking at, and then they come along and they look at some kinematics because they've got no further way to go really with the dynamics. So they start looking at the alignment between the vorticity vector and the strain rate eigenvectors. So you have this dynamic analysis that you've seen up to this point, and then a kind of kinematic approach trying to understand the alignment structure. And it's quite common to see this in a lot of the papers. And the key result in this field was from Ashurst et al. 87, where the vorticity vector was preferentially aligning in homogeneous isotropic turbulence, but also in many other flows, with the intermediate strain eigenvector, which is really counterintuitive, actually. You would anticipate from Taylor's arguments in the 1930s, it would be aligning with the direction of maximum extension. And from Betchoff's arguments in the 1950s, the opposite, it would be aligning with the direction of maximum compression. For it to going with the other direction was definitely counterintuitive and doesn't sit with a kind of eigenvalue picture of the universe you'd anticipate, therefore, with the compression or the extension. And so what motivated me to look into this was to sort of think about this and not be really happy with the fact that one has to do some dynamics and then some kinematics. Can we put all of this into a dynamic framework and work with it then appropriately? And that's what I attempted to do in this paper, where we're using the Schur decomposition instead of the eigenvalue decomposition. Now, the 2 transforms are identical if it were the case that the velocity gradient tensor was unitary. Basically, your standard inverse on your eigenvalue transform is replaced by a transpose in the Schur transform. So if the velocity gradient tensor is unitary, the inverse and the transpose operations are equal, and so there's no difference between them. So that would therefore be a unitary VGT, one where you can replace where the transpose is operating and it doesn't affect your matrix multiplication. So here's a symbolic representation then of a standard eigenvalue decomposition where L are our eigenvectors, and we've got that acting on our diagonal eigenvalue matrix. So the Schur transform, as I've already said, replaces that inverse with a transpose. So we then have this form of the equation, where now we've got these unitary rotation vectors, which are simpler in structure than the eigenvectors. Because we've made those rotation vectors simpler, not so surprisingly, the middle matrix is now more complicated. However, it's still related to what we get in the eigenvalue one, because we have sitting on the diagonal the eigenvalues, but we now have this upper triangular part, n. And in fact, if we work with a complex transform, that's strictly upper triangular. We don't kind of fall below the diagonal at all. If you do the real valued one, you do fall below the diagonal. For this talk, I'm going to work with the complex one just because it makes notation easier. And because everything I'm working with ends up being a trace or a determinant anyway, it all comes back to the real world when you do that operation. So mathematically, it's much easier to work in the complex form. If you wanted to do individual rotations, and there's been a lot of work out of Texas Tech, for example, using this approach for coherent flow structure identification, then you're working without these trace operations. Then you do need to use the real transform, but the trigonometry becomes a bit of a headache to just keep track of. It's much easier to do everything in complex with the complex transform, particularly, as I said, for our purposes where we're working with traces and things. But what this allows one to do, therefore, because of that separation of t additively into a diagonal term and an upper triangular term, we can define two matrices B and C by applying the rotation vectors back on the eigenvalue part and the upper non-normal part. So in other words, we end up with a nice simple equation that A equals B plus C. So if we then start to look at the consequences of that decomposition by putting it back into the terms that we've already defined, then you notice, for example, that why is it the case that Q can be expressed solely in terms of the eigenvalues? Well, the two terms in Q, the entropy and the total strain, can be written as in terms of their normal or eigenvalue equivalents with the B subscript, and this non-normality term that appears on both. So of course, when you take the difference, it cancels out, and we're just left with effectively omega B squared minus SB squared. So that explains why Q works as an eigenvalue term in a kind of roundabout way. And the same thing applies for R, except here we now create two terms. We have negative det SB, which is the eigenvalue normal equivalent to negative det S, as it were, because also appearing on both equations, on negative det S and on trace omega squared S, are these two extra terms that again cancel when we do the subtraction. So we've got this interaction term between the non-normal entropy and the normal straining, trace omega C squared SB, and then we have a purely non-normal term, negative det SC, as well on the far side. So again, in a roundabout way, this shows why these terms can be written in terms of the eigenvalues. Not that you'd ever do it that way, but it makes the point. But what it also therefore shows is that there's these new terms that we can explore the physics of if one does the Schur decomposition approach. So first of all, is C just irrelevant? If all of the action is in the eigenvalues, then who cares about any of this? So to start off with, I've defined this little index down the bottom left there, kappa BC, as the normalized difference in the norms between the B and C in the tensors. And this is for the Johns Hopkins turbulence HIT database at Taylor-Reynolds of 433. And the key thing is just to notice why the modes of these distributions are typically close to zero. In other words, the non-normal contribution is actually as big as the bit that's in the eigenvalues. So if your analysis is purely focused on Q and R, in other words, that diagram that we've already looked at with the regions, you're missing, in a sense, half of the physics, because roughly the mode of this distribution is sitting at zero in the middle. But you'll also notice there's a slight tendency, for example, in region 3, that is, as we cross the discriminant function and start gaining some local vorticity, the eigenvalues have become complex, that this is significantly negative. It's also slightly negative in region 2. By the time we get down to region 6, on the Viefos tail, remember on Cantwell's formulation, that's where everything ends up. We've then got a dominance of normal dynamics, and you'll see the mode is slightly positive in that region. So where everything kind of ends up with Cantwell's model, we do get a dominance of the eigenvalue type processes. But where we're starting to try to create local vorticity on that transition from region 4 to region 3, and then grow it with positive entropy production into region 2, it's actually negative. Okay, so that's HIT. But in fact, if you look at spatially developed kind of real flows for the engineers who are listening, then actually this term is even more important. Here's some work from Paul Beaumel's master's thesis on this. First of all, some data from a cylinder wake experiment. He's kindly included my original figure from the last diagram as a dashed line, and you can see that at various distances downstream of the wake, d is the diameter of the cylinder, so he went from 0.1 to 3 diameters. The plots are very, very similar for all of those distances and always more biased towards C. So the non-normal processes are more important, it would appear, in real flows than they are in homogeneous isotropic turbulence. There's a mixing layer case that's shown on the right, and the key thing is this really close region of the mixing layer, the black line. You can see it's very, very strongly negative on this diagram. There's also an instance when we get over, it is sort of intermediate distances downstream. These results are non-dimensionalized by the splitter plate thickness, which I think I had as H there, but because you're all from over that bit from where I am, I think I put an H as for the normalization there. You'll see that some of them, around about 90 to 100 or so in the bottom right, actually have this bulge again in region 6, showing more normal contributions than you might anticipate from HIT, but very close in, more non-normal contributions. So what this is actually showing is that, what's the physics then behind this mathematics? This is showing that the manner in which the non-local contribution from the pressure Hessian, due to shear dynamics, is affecting pure straining and pure rotation. Because really the eigenvalue components are about those pure motions, and as soon as we put the shearing in, that starts mixing things together. And of course, what we've done is we've made that explicit, because mixing things together is precisely what is happening on this term trace omega c squared SB, where the normal straining is acting directly on the shear-induced rotation component. And that is where some of this complexity in turbulence is going to come from. Okay, so this wasn't my work, but some people have taken this idea on, and you can see again it's the same kappa structure. But this is a multi-phase flow, perhaps of interest to colleagues working on combustion or similar. So you've got these inclusions of non-vaporized liquid in a gas flow, and you can see again that when we're close to it was a cylinder and a mixing layer on the previous slide, here it's close to these inclusions, more of a dominance of the non-normal dynamics again, as shown by that displacement of the black line towards the right-hand side. So the subscripts here were sort of close, intermediate and far for the different plots. Okay, so moving on then, we've already noted that a really important result in turbulence theory is this alignment between the vorticity vector and the intermediate strain eigenvector. So how does it come about? Well, notice that now we've done our decomposition, we've actually got a classic vorticity vector omega A, but we've also got an omega B and an omega C. So we can look at the alignments between those. And we've also therefore got different strain eigenvectors as well, A, B, and C. And so what I'm showing on this diagram is the alignments between the different vorticity vectors. So you can see that the example that's given in the bottom left, the notation A, B, it's omega A with omega B. And there's a key difference that you can start to see is that in regions 3 and 5, where we're just above the VA-FOS tail, we have a completely different dominance of that relationship relative to when we've got strong normal vorticity starting to develop in the upper part of the QR diagram, where the black line is starting to dominate. So there's a real transition here, and this is partly why I like to use 6 regions and not 4 regions, because there's a massive difference here, as you can see, in terms of the alignment structure between these different vectors that wouldn't be captured if you took the mathematical approach and merged together these 2 different regions. So why does this result happen? Well, where Q is less than 0, it comes about because of this alignment of the strain eigenvectors with the non-normal part of the vorticity. There's a complete dominance on this diagram for regions 3, 5, 4 and 6 by this red dot dashed line, which is conveying, if you look at the notation here, you've got, as an example given on the left-hand side, omega A E for the strain eigenvectors, I, which one it is, 1, 2 or 3, and then B or C for which tensor we're talking about. And you can see that there's a complete dominance here with the non-normal part of the vorticity, omega C, and then the strain eigenvector always being the intermediate one. So that is why this is happening in those regions. And where Q is greater than 0, it comes about because of this strong mutual alignment of the strain eigenvectors. So on this diagram, what I've done to start off with is I've found all of the tensors where there's a strong alignment in the vorticities. So all the results are conditioned on that value being greater than 0.985. That means plus or minus 10 degrees perfect alignment is what that translates as. And you can see that in every single diagram that's shown here, the ones that have eliminated because they only constitute 0.7% of all the occurrences, each graph here, the largest bar is a light grey bar. And if you look in the bottom corner, J equals 2 is the light grey, and that is therefore corresponding in this notation to the intermediate strain eigenvector for the terms we're looking at here. So if the grey bar is on the left-hand side, that means I equals 1. So we've got a coupling between the intermediate strain eigenvector on our non-normal tensor and the most extensive on our normal tensor. If it's over on the right-hand side, then I equals 3 based on the diagram on the bottom right. So there's a coupling with the intermediate non-normal tensor and the most compressive normal eigenvector. But remember, when Q is positive, by definition, Q is entropy minus total strain is positive. That means total strain is small. And from what we've already said, because the non-normal terms subtract, that means that the term that is giving the I here, which is either the 1 or 3, the extensive or the compressive, is going to be small in magnitude by definition of Q being positive. So it's coupled to an intermediate strain eigenvector in C that is not controlled by whether or not where we are in the Q diagram. So it can be very, very large. And thus it dictates the overall strain alignment, because you've got an intermediate one for C that is larger in magnitude than an extensive or a compressive one for B. And thus we can explain why we have this classic result of a preferential alignment with the intermediate strain eigenvector. It's due to this coupling between what we would expect for the eigenvalues, but they're small in magnitude, but it's the intermediate eigenvector for C that is dictating what's going on. Okay, so based on these results, we then decided to try to explain and look at turbulent structure a bit more detail. One of the first things that we did with this is looking at this QR diagram and trying to discover what the sort of natural regions are in this diagram. So we've already said that mathematicians and engineers disagree on what the natural regions are. I've already said that I disagree with both, and I'd rather have 6 regions. But there are other approaches. For example, there's a really nice paper by Arkady Sinoba, Beat Luthi, and Marcus Holzner about 15 years ago, where they suggested that you should look at the sign of Q and then split out separately your signs for your production terms. Not look at R in total, but look at the two separate terms that constitute it. So that's another classification. Because all this conditional analysis is a bit difficult to do, we actually tried to do this using a network for the turbulence, so that rather than having infinite conditional distributions all to the power of something, because we're conditioning on lots of variables, in other words, we're not working, rather than needing data that's sort of infinity to the power of however many dimensions we need, we worked with this network that allowed us to simplify things down to 844 discrete nodes. And we then tried to find which was the best classification, and it transpired that region 6, this one with 6 regions, worked well. Actually, Marcus Holzner's one worked really well as well. Both better than the simpler ones that we've referred to earlier, the sort of mathematicians one and the engineers one. But to improve them, the key thing to include was omega c squared and its relative magnitude to the other 2 terms, that is omega b squared and sb squared. And this little visualization is the QR diagram with a third axis added, showing the properties of this sort of non-normal term, the other term in there, and how potentially it might lead to perhaps a slight rethinking of this QR diagram, because yes, you can look at it in this plane, as you can see top left, but there's some interesting stuff happening kind of going into the page behind it, as you can hopefully see from this visualization. Some other people who've been interested in this are people in aeronautics, and this is work from Imperial College Aeronautics looking at the wake region of a Nacre airfoil. So this is DNS work on this airfoil. In particular, if you notice in this diagram in the top left, there's a transect longitudinally B and a transect vertically A. And so on this diagram, you can see the flow for the recirculating flow, that's along that transect A, and then a kind of downstream X over C transitional region after that immediate recirculation region, which is along that transect B. And you can see different contributions here using this decomposition of mine. And you can hopefully see that omega c squared and sc squared are identical, which is why earlier on I substituted out sc squared, and I just talked about omega c squared because it's a mathematical consequence. It has to be identical. So this is what they started off doing in this paper that was in JFM last year. But then they also started looking at the different regions on the diagram, and in particular started noting, for example, if you look here, you'll see this is the entropy production in the top 2 panels and the strain production in the bottom. You'll see that the blue line, region 6, this VA-FOS tail region is really important for the strain production. But when you come up to the entropy production, it's region 2. And that all makes sense from classic ideas. Again, Q is positive in region 2, Q is negative in region 6, and they're both centers of probability. That all follows through logically. But what they then did was try to break these terms down using my equations that you've just seen earlier. And now you can start to see some differences appearing in terms of which the particular terms are important. So you can see that for all QR regions, which is the overall behavior seen in the top row of panels, you'll see that the most important term is the blue line, while down in region 6, it's the yellow line. So there's a difference here in terms of what we're seeing by virtue of the preferential normal dynamics in region 6. But when we're in the other regions, we've got this dominance of this interaction term, this term where it's the normal straining of the shear-induced vorticity that dominates the dynamics. And if we look at the same for entropy production, again, we've got the recirculating flow, the transitional flow, all QR regions, and again, this time region 2, because that was the one that was dominating. And you can again see there's some difference here, where again, in region 2, it's the normal dynamics, omega B, SB, that's dominating. But when we look at all QR regions combined, we get a dominance again from this interaction term, this shear-induced vorticity being produced by the normal straining. And you can actually start to then see why perhaps equilibrium turbulence models might start breaking down for these kinds of problems. Because if you look at this, there's a spatial separation between how these terms are contributing to these dynamics that will be difficult to accommodate with a conventional turbulence closure. Hence, this is DNS. If we zoom in, on that top right diagram that we were just looking at, we can then actually see that if we were doing conventional analysis, all we would have is the pink line. It looks like a pink and blue dashed line because they're just showing that the sum of the terms from the decomposition is identical to the pink line. However, if you did do the conventional analysis, you'd get these three peaks in your results that wouldn't be perhaps very obvious to explain. Why are the three peaks at roughly 1.3, 1.4, and 1.6 distances downstream from the wing, chord lengths down? Well, we can then explain this. First of all, we've got this peak coming from this normal term. We've then got a second peak coming in from this interaction term between the shearing term and the shearing driven by the normal straining. And then we've got a final peak coming from the normal term again. So again, doing this decomposition gives you some physical insight into a result that isn't at all obvious to explain using conventional analyses. And so this perhaps suggests that there's some interesting displacement again between how entropy is being produced, because it seems to have an initial surge, then a gap, and then it comes back. And that gap is kind of infilled by this interaction from the shearing that's giving us this secondary peak. And this spatial separation in this production is clearly of physical significance. And it would be great if turbulence models could kind of capture this behavior implicitly. Okay, so another bit of work that I did in this area was, again, a boundary layer, although in my case I did it for a channel flow. But I started off with an equation, an analysis from Susumu, Goto, and Motori from JFM in 2019, where they basically did a Reynolds decomposition of the entropy production equation that we've already been looking at into its mean and its fluctuating parts. And with the symmetries in a boundary layer, you end up with this expansion into these three terms. What I then did was I said, oh, okay, let's try and do this with this decomposition into the normal and non-normal terms. And you get this quite large expansion. But what you can then, of course, do is go into your DNS and say, well, which of these terms are actually worth looking at and important, and which ones are actually doing nothing whatsoever. And here is the primary diagram from this paper. Note, first of all, that the purely fluctuating term on the right-hand side is the one that dominates far from the wall. The black lines are the lines from the Motori and Goto paper. Well, they are identical to the ones from the Motori and Goto paper, but they're my generated ones. And you can then see they're decomposed below, and I've just shown the terms that are important from that full decomposition on the previous slide. And again, the decomposition is useful for explaining these results. For example, they never had explained in their original paper why this middle diagram goes negative, switches positive, and then asymptotes back down to zero. But you can see why on this diagram, because we have the purely non-local or purely non-normal term, CSC omega C, negative at first, going slightly positive and then asymptoting, while this term, which involves a fluctuating omega B, is basically largely positive throughout, but only switches on at about y plus greater than 5. Hence, we get this switching behavior that you can observe. And similarly, we can see the similar pattern and explanation for why we have this double peak in the diagram on the right-hand side. They couldn't really explain that double peak, but you can see that once we've done the decomposition, the purely non-normal term is contributing at a different height to the one that's involving an interaction between the normal and non-normal contributions, and that then leads to this double peak into the entropy production away from the wall. And again, if you're interested in control theory, for example, you're going to be wanting to try to do something about what the vorticity is doing in the boundary. And so these results potentially are informative for thinking about control strategies. And that approach is just shown visually here, the same snapshot and just different terms. So in the top left corner, I've got the sum of the two terms that were most important. So this is just the fluctuating term, and we've got omega c SB omega c. It's that normal straining of the shear induced vorticity, and the other one is the pure non-normal term. And you can see overall the budget is positive, as you'd expect. But one thing that was interesting is the reason that omega c SB omega c dominates the budget, even though there's lots of shear near the wall, is that some of the terms that are the purely non-normal ones contribute negatively in the mean. So you'd expect near the wall where shear dominated, that should be driving the budget, but it doesn't, because some of the terms are negative in the mean. And you can get an insight into this a little bit if you compare the snapshot in yellow, which is the interaction one, omega c SB omega c, and the one in red, which is the equivalent for when it's purely non-normal. Everything's got a C superscript. And this is the transverse component. So this is straining motions that are transverse with a vorticity that's going along the bed with a transverse axis. And this is the dominant component. And you can see in both cases the standard deviations, which is the number in brackets, is quite large. But the average value for the one involving the normal straining is quite a bit bigger and positive. And you can kind of see that visually on the diagram. There's more blue contributions from that term than the other one. And so just from these snapshots, even though it's instantaneous, you get a feel for the reason why the budget works the way it does. Because, as I said, some of these purely non-normal terms contribute negatively in the mean. You can almost see that in the panel C, for example. There's lots of red and very little blue for the one that's involving contributions downstream and vertically, involving purely non-normal terms. Okay, and a more recent piece of work with collaborations in civil engineering at Imperial is looking at turbulent jets, which obviously are important in a wide range of applications, urban flows, for example, and also obviously industrial processes. And the starting point for this analysis is an approximation to the pressure Hessian, not using pressure Hessian related terms, which has been the whole spirit for today, right? We've been trying to capture the pressure Hessian implicitly in this non-normal term C. And so they write down the classic equation for total strain, and then they make an approximation. They say, we're not going to look at the transient term, and we're not going to look at the viscous term. In which case we can approximate the pressure Hessian by the sum of the entropy and the total strain. And if anyone does coherent flow structure visualization, you'll have used this, because lambda 2, the second eigenvalue of this thing, is what you're using to then identify coherent flow structures if you're using the lambda 2 criterion, which comes directly from this paper. Of course, if we make that approximation and we do our expansion, we actually get 6 terms. And recently in a JFM paper, Alain Poumé and Yang have suggested that the entropy term, which for us is terms 1, 3, and 5, is sufficient. But note, in principle, therefore, we could actually do better, because we could use fewer terms than implicitly the 3 terms that Yang and Poumé used. In the next diagram, I'm also going to make use of a term chi, which arises from a way of looking at the pressure Hessian by normalizing it to get this Hij, and then essentially taking the second invariant of the normalized pressure Hessian, deviatric pressure Hessian. That's chi. So on the next diagram, I'm going to be using delta, which is the discriminant function from earlier. So more positive it is, basically the more coherent structure like the flow is. If it's negative, we've got real eigenvalues on the velocity gradient tensor. And this term chi representing the pressure Hessian. And I'm basically going to look at the alignment between this approximation for the pressure Hessian and the pressure Hessian itself. And I'm doing this as a function of distance from the edge of the jet, top left corner, Z negative 9.75, right on the very margins of my jet, right onto the center line, Z equals 0, which is the bottom couple of panels. You see, we start off, delta is based in top left, delta is very close to 0. We don't have, on average, much coherent motion. We're right on that edge of the jet. Chi is typically strongly positive, which means a dominance from the deviatory part of the pressure Hessian, or C, in our terminology. And you'll see, first of all, that the Zhang and Hossein approach has a strong maximum at this 0 for delta, close to 1 for chi. All of the other approximations listed are very, very similar to it, but the Yang and Pumir one doesn't do very well because we haven't yet developed any real strong vorticity. As we move more into the flow, Z equals negative 9.5, Z equals negative 9.25, we start to move away from chi equals 1. We start to get more isotropic pressure Hessian contribution, i.e. B becomes more important. And at the same time, vorticity becomes more important, delta becomes positive. Then, as this happens, you'll see at Z equals negative 9.25, all of a sudden the Yang and Pumir approximation based purely on entropy starts doing really well. But note, just right next to it is the green dotted line, which is my approximation, where I just take the normal straining motion and the shear-induced entropy motion. So now 2 terms, not the 3 terms that Yang and Pumir have got, all of which are entropy related. As I have to I make a scale change by a factor of 10 when I go to Z equals 8.75, and I make a scale change by a factor of 20 to get to Z equals 0. And when we get to Z equals 0, yes, the Yang and Pumir approximation is doing extremely well. Fascinatingly, it actually does better than the full term, where chi equals tends to 1, which you'll see is the blue box. In other words, by throwing away the straining terms, you're actually capturing something of the transient straining term that was eliminated in the model. But note, the other term that's asymptotically doing well in that respect is again this green line, the normal straining plus the non-normal entropy. So why Yang and Pumir models does well is because of the effect of this, not pure entropy, pure rotation, it's this shear-induced component that is where we're perhaps seeing the action of the transient term in the strain equation that leads us to this better than the approximate, using less terms than the approximation, we get a better approximation than the full approximation, which is somewhat fascinating. And just to finish, I'll just talk a little bit about 2 modelling approaches. First of all, I'm going to look at the stochastic differential equation model to try to mimic QR dynamics. This is given in the equation on the second block, where we've got approximations to all the terms given as a tilde, and you'll see a df term on the end, which is a Gaussian forcing term, and then there's some coefficients pi. Note that pi 3 is the Reynolds number dependent coefficient, and it's the one where the non-normality is going to come in because of this interaction between S and omega. Again, to study these dynamics, we used our network to reduce the degrees of freedom down from needing trillions and trillions of points to be able to do the dynamics on 844 nodes with just literally tens of millions and get converged results. And this identified some new pathways in turbulence. But what I'm going to focus on here is the nodes in our network that link together the different regions of the diagram. So in the legend, you'll see 1 to 5 and you'll see 5 to 1, the nodes that are mediating those fluxes of the flow from different regions. And you can see the DNS on the left and this enhanced Gaussian closure, the SDE model on the right. Now, first thing to note is that in terms of replicating the PDF, the EGC model does a fantastic job. But when you get into the nitty-gritty, as we are here, you can start to see some systematic problems. To start off with, where does it do really well? Well, it does really well in the transitions between regions 1 and region 2. It's got the magnitude about right. It's got the right number of vertices acting as well, approximately. Roughly, it's a bit better, and the DNS uses slightly fewer nodes, but it's pretty good. However, when we start looking at some of the other things, we note some real big differences. Exchanges from region 6 to 4 and 5 to 6, they're not concentrated on key nodes. Look here, for example, at this first instance, you'll see the largest node is about 100 times weaker on the EGC. Note it's a log scale. It's about 100 times weaker than it is in the DNS. And when we come out to the other case, 5 to 6, you'll see it's about a factor of 20 weaker. Another way things are wrong is they're too diffusive in the EGC because it has to use too many nodes. Note that in the DNS, there's only one case where we go out beyond 60 nodes. Well, you can see both in this particular instance and shown here, we're going out to many, many more nodes in the enhanced Gaussian closure. That Gaussian forcing term is doing too much work. And what I would like to therefore do is go back to this equation, and this is sort of current work, and then try to put the non-normal normal dynamics in explicitly so that when we do get to the Gaussian forcing, it's not having to do quite so much work. Because if we look at the second statement that I just made, and I'll come back to it now. It's also worth noting that from 1 to 5 uses too few in the EGC. But 6 to 4 and 5 to 6, they were not concentrated on enough nodes. And note that those are the regions where we're crossing over key boundaries in the diagram. We've got to go from region 5 with complex eigenvalues to region 6 with real eigenvalues. That's very difficult for the model to do. And again, it suggests we can use the non-normality if we put it in the model explicitly to mediate those dynamics. And the final example, I haven't had time myself because I struggle to recruit. I'm in civil engineering and I really can't find any PhD students or postdocs really. So I tend to just do everything on my own. And as a consequence, I haven't had time to fully code up an SGS model, but I was quite shocked how effective this very simple implementation of these ideas was by some colleagues in China in a paper in Phys Fluids in 2021. Their capital K here is my index kappa from earlier. And you'll see they've conditioned Q and R and the SGS dissipation with Y plus distance from the wall. And this is now a compressible boundary layer. So P is non-zero, but they focused on Q and R. And they've noted that the SGS dissipation is different for the normal dominated regions and the non-normal dominated regions. Remember, the non-normal dominated is the red line here, it's K is negative. And what they decided, therefore, was based on this difference in the SGS dissipation, they would rewrite the classic Smagorinsky model. It's implemented in the dynamic form, but it's obviously underpinned by the classic model. And what you can basically see in this equation is it's a mixing model, effectively. It's the classic Smagorinsky principle. You've got a coefficient and you've got your straining, but they've mediated it by having two Smagorinsky coefficients, effectively, one for B and one for C, acting on the normal straining and the non-normal straining. They've got an overbar on their density because they've got a compressible flow. And here's their results. And you can see this classic Smagorinsky model being overly dissipative is shown. It's really not capturing the physics at all well. The DNS, though, is really nicely replicated by just this simple change to the classic Smagorinsky model to make the normal and the non-normal dynamics explicit. So if you're much more on the applied end of things and have thought a lot of what I've been talking about today is really sort of slightly abstract maths and physics, hopefully this result brings home that this stuff, I think, is very important from a practical perspective. Okay, so thanks very much. Here's a few summary points then. So I think that adopting the Schur transform gives us a new approach to doing these things, because rather than kind of hiding things in the kinematics of alignments, we have new terms in the equations which we can then study. And hopefully today I've convinced you express themselves in some interesting ways in a variety of flows that's worth getting an understanding of. Non-normality is as important as normality. We can't just say it's just the eigenvalues, it's just Q and R. The magnitudes do not bear that out. The deviatory part of the pressure Hessian, as represented here through the non-normal dynamics, is just as important. Using the decomposition, we can explain some of these results. I showed you some results from George Papadakis's group on the wake of a Naka airfoil and this multi-peaked form to it. Also some results from Susumu Goto's work on boundary layer structure away from the wall and this change in sign of one of their terms, for example. So we can explain a number of things, and hopefully I think it will going to lead to improved stochastic differential equation models for the dynamics in the spirit of the Michael Wilczek Charles Menneveau model, but also subgrid scale closures, particularly for LES, maybe a little bit for RANS as well. Okay, thank you very much.